Okay, this is going to be the first of two videos for your spectrometry lab. I've already covered this in lecture, but I'm going to cover it again for the lab. So, spectrophotometry is the goal is to understand and use principles of spectrophotometry to determine the concentration of a colored compound or ion in solution. It's a method of analysis commonly using electromagnetic radiation, where you commonly use infrared, visible, or ultraviolet radiation. And spectrophotometry usually refers to visible light. So visible light has wavelengths of approximately 650 nanometers to 400 nanometers of wavelength. So this symbol, which looks like an upside down backwards Y, is the symbol for wavelength. And you say this, the Greek word for this is lambda. And the 650 nanometer is a reddish color, and the 400 nanometer is a violet color. And you can remember the order of the colors in the rainbow by this Roy G. Biv, or you can flip it in reverse and it's Viv Gior. So when you have an incandescent light that gives off white light, it actually gives off a rainbow of colors. You pass it through a slit to get all the light oriented in the same direction, pass it through a prism, and you get the different wavelengths of light coming out of the prism. So here, since I happen to have a red, green, and blue pen, I used red, green, and blue. Now, coming through a solution, these lights might be absorbed by the solution differently. What absorbs the light? The molecule does. So in this situation, the red light was not absorbed very well, the green light was absorbed kind of well, and the blue light was absorbed very well. So here we would say that the red light was transmitted. Now, if it's transmitted, meaning it manages to go through the solution without being absorbed, the solution is going to look largely red. So when you get the absorbance spectrum of this, the absorbance spectrum looks like this. Now, the absorbance is the opposite of transmittance in a way. Transmitted is how much light gets through. Absorbed is how much light gets absorbed or stopped. So if all of this red light gets through, very little gets absorbed. If a little bit of green gets through, a little bit gets absorbed. If just a little tiny bit of blue gets through, a lot gets absorbed. So this is what the absorbance spectrum would look like for the Roy G. Biv absorbance spectrum at our detector. So transmittance. Transmittance is a measure of how much light gets through a sample. And if this is the incident light and its intensity, and this is the light that comes out, the transmitted light and its intensity, the ratio of P to P0 is transmittance. And the values for transmittance will range from 0 transmittance, meaning no light gets through, to 1, where all the light gets through. So if this is 20 and this is 20, all the light gets through. 20 over 20 is 1. People talk more about percent transmittance than they do transmittance. So to get percent transmittance, you take the transmittance and multiply by 100%, just like you do for any other thing to get percent. You multiply by 100%. So that means transmittance will range from 0% transmittance to 100% transmittance. 0% transmittance means no light gets through. 100% means all of it gets through. Now, normally we don't talk about whether or not light is getting transmitted. We look at whether or not light is being absorbed, because we have something called Beer-Lambert's law, which includes absorbance but not transmittance. And the reason for that is Beer-Lambert law is a linear relationship. And if you try to make a Beer-Lambert law with transmittance, it's no longer linear, it's logarithmic. So absorbance is the negative log of transmittance. And that's what you really need to know. This is just other stuff that you can look at later. So the Beer-Lambert law simply says that absorbance is equal to the path length times the concentration times the molar absorptivity. The path length is the length of solution that the light goes through. Naturally, if you double the length of solution, you will double the number of molecules you run into and double the amount of light absorbed. So absorbance is proportional to path length. Naturally, absorbance is proportional to concentration. If you have a solution of 1 concentration and light gets absorbed. If you double that concentration, you will double the number of molecules the light runs into and double the amount of light absorbed. So absorbance is also proportional to concentration. Now, it turns out that absorbance is also proportional to this molar absorptivity. This is a physical property of the molecule that depends on two things: the molecule itself and the wavelength at which light is being absorbed. Because it turns out that not all light is absorbed equally, as we saw in the previous slide with that absorbance spectrum. To do an absorbance analysis or a spectrophotometry analysis, the things you have to do is you have to calibrate the spectrophotometer. You have to set the zero absorbance and set the complete absorbance, so complete transmittance or no transmittance. You obtain a spectrum for a sample and determine the optimum wavelength for the experiment. And that wavelength is going to be where the absorbance is the greatest. You want a great absorbance so that when you get half the concentration, you can see that you got half the absorbance. So if you have a very small absorbance and you get half the absorbance, you see that. So you can see that it's really hard to see that there's much of a difference. So you work at a wavelength where absorbance is the greatest. And then you construct a calibration curve. Calibration curve is where you determine absorbance and concentration data for solutions of known concentration. And you construct a curve that looks something like this. So here's absorbance, here's concentration. Naturally, if the concentration is zero, you expect absorbance to be zero. If the concentration is here, when you double the concentration, you expect to double the absorbance. And so you construct a calibration curve. And then you get the equation of this line. And then when you submit a sample to this analysis, once you have the equation, so A equals MC plus B, where C is equal to A minus B quantity over M, once you get the absorbance of an unknown solution, you can plug it into this formula and get its concentration. Now, the molecule we're going to be using in this particular experiment is something called bromothymol blue, and it changes color depending on the pH. And you're going to see a nice diagram in the lab write-up about this, or the lab notebook part, that shows this bromothymol blue. So what I want to show you about this is what these lines represent. So it turns out that these lines all represent bonds. So you see this line right here that I'm pointing out? That's a bond. You see this line that I'm pointing at? That's a bond. You see this line I'm pointing at? That's a bond, and so is the one right next to it. When you have two lines that are side by side, it's called a double bond. The single line is called a single bond. Guess what 3 lines is called? It's Cub Scout salute. Okay, it's a triple bond. All right, so we don't have any triple bonds here, but we see lots of bonds here. And we kind of wonder, what is the bond between? If you take a look here, it's obvious this bond is between sulfur and oxygen. That's very obvious. But what about this bond between sulfur and this structure here? What's going on there? And that's why I've redrawn this over here so I can show you what's going on. So here, obviously, this is a sulfur-oxygen bond. This is a sulfur-carbon bond. So the deal is if we don't have an atom at the end of the line, it's a carbon, period. So do you see at the end of these 2 lines, we don't have an atom drawn? It's a carbon. You see at the end of this line and where these 2 lines meet, there's a carbon. Where these 3 lines meet, there's a carbon, and so forth and so on. So every place you see an end of a line and you don't see the atom represented by a symbol, it's a carbon atom. So I'm going to fill in carbon atoms here. You'll notice at the end of this line, we have a bromine, so I'm not going to write a carbon there. And I'm going to put carbons all over the place. You see this line here, it ends. What is the atom there? It's a carbon. So I'm just going to fill in all the rest of the carbons. And now I'm going to fix a few more things. You see this HO here? Well, here, if I wanted to draw that, I would show a single bond to hydrogen. And that's because hydrogen only makes single bonds. So the same for this OH over here, it'd be like that. And you'll notice when we have this HO and this OH, they represent the same thing. We've just kind of drawn them a little bit different as far as the angles go. Now, there are some atoms that are missing. Oh, I missed a carbon here. And here, there are a bunch of hydrogen atoms that are missing. The deal is every carbon atom has to have exactly 4 bonds, 4. So take a look at this carbon. It has 4 bonds, 1, 2, 3, 4. So it's good. But look at the carbon below and next to it. It only has 1, 2, 3 bonds. It has to have 4. So what do I do to make it have 4 bonds? I add a single bonded hydrogen. Remember, hydrogen only makes single bonds, and that's it. So now that carbon has 4 bonds, and I've completed that part of the structure. And now I've completed that one, and that one. And this carbon already has 4 bonds. It's good to go. This carbon has 4 bonds. Now I'm going to add hydrogens to carbons that need them. And there's one needed here, one needed here. And now what about this carbon here? Well, that carbon only has 1 bond to it, so I need to add 3 hydrogens. Now it's going to get a little tricky in here if I do that. So I'm going to draw this like that, CH3, to represent 3 hydrogens, each singly bonded to the carbon. And I'm going to do that wherever I need it. And there we go. And so now I think I've completed the structure of this. Oh, I see I'm missing 1 hydrogen right there to that carbon. And each carbon has 4 bonds. Each hydrogen has a single bond. The oxygens have 2 bonds each. The bromines have 1 bond each. And the sulfur has 6 bonds, which is normal. Okay, so I've completed the structure. And we could actually count up the atoms and get the formula of this compound. 1 sulfur, 1, 2, 3, 4 oxygens. How many bromines? 1, 2. How many carbons? Well, I'm going to let you figure out how many carbons and how many hydrogens. So this is the molecule we're going to study. You're going to see a diagram in the lab notebook that shows you the different structures. That's something I probably would not write into my lab notebook just because it takes too much time. But the different structures confer different colors on the solutions depending on pH. Okay, and that's the end of half of our intro. The other part will be the demonstration portion of the lab. Okay, thank you for listening.